All right, welcome back. We're going to continue to be looking at systems for the next, well, at least this lesson. They'll come back again in the form of inequalities in a day or two, I think. But what we're going to look at today is using the process that we looked at yesterday called elimination to solve larger systems. So specifically, we're going to look at systems with three unknowns. So if you have a system that has three unknowns or three variables, then it has to have three equations for us to be able to solve. So for every variable, we need an equation. It's the only way we're going to be able to solve a system like this. And then the solution, just like we saw yesterday, is going to contain a value for each of the variables. So yesterday we looked at linear systems. We had two equations, two variables. Those variables were x and y, and so our solution had a value for x, a value for y. And now you can see in this 3x3 system, we've got three equations, three variables, and it's x and y and z. So if we're looking at this first example, just to verify a solution, we know we can plug the solution in. It's got to make each of the equations true. So 5 represents the value for x, -1 represents the value for y, and -2 represents the value for z. So we're going to check this by plugging in 5, -1, and -2 for x, y, and z into each of the equations. So I'm going to start with the first one. We'd be looking at x, which is 5, plus 5 times y, or -1, plus 5 times z, which is -2. And if this checks out, all of that should equal -10. So we have 5 minus 5 minus 10. And the 5 and -5 cancel. And in fact, -10 does equal -10. Now let me check with the second one. With the second one, x plus y plus z. So 5 plus a -1 plus a -2 should all equal 2. And that's 5 minus 1 minus 2. And 5 minus 3 is definitely 2. So 2 equals 2. It checks out there. And then the third one, let's call this number 3 here. X, which is 5, plus 2 times y, which is -1, plus 3 times z, which is -2, should all equal a -3. So 5 minus 2 minus 6. And 5 minus 2 is 3, and 3 minus 6 does in fact equal a -3. So we verify that 5, -1, -2 is the solution to that 3x3 system. So again, your 3x3, three equations, three variables, and it's going to have a value for each of those variables. Now we're still writing it in something that looks like an ordered pair. It's just the x value, the y value, and then the z value. Okay, now this one obviously can't be solved by graphing. Because these aren't lines. We're not going to be looking for a line where these things cross, although I can show you something a little bit later in Desmos. But for now, we're going to look at solving algebraically, and the process incorporates the elimination that we looked at yesterday. So the goal is to get the 3x3 system that we start with, this 3x3 system that we start with, down to a 2x2 system. If we can get it to look like something that we saw yesterday, then the elimination becomes pretty straightforward. So to get the 3x3 down to a 2x2, we're going to choose two of our equations to eliminate a variable. And it doesn't matter which two equations we choose, and it doesn't matter which variable we choose. We're probably just going to, see what jumps out to us. So we can choose to eliminate x's or y's or z's for this first step. Now in the next step, it's very important that we choose two different equations. So we choose two different equations, but eliminate the same variable. Okay, so in this step here, we choose two equations. Any two equations, we pick a variable, we get rid of it. Use elimination. And then in the next step here, we're going to choose two different equations but get rid of the same variable. And the result of those two steps, the result of those two steps is going to create for us the 2x2 system. So it'll look like what we did yesterday. And then we use elimination again and back substitution to continue to solve. All right, so let's look at this first example. And just for organizational purposes, which is probably the most important aspect when you're dealing with these problems, I'm going to label these equations A and B and C. Okay, so whatever jumps out at us, it looks like, if I'm looking at these, since all of the x's have coefficients of 3, multiplying by a negative would make it pretty easy to eliminate that variable. So I'm going to choose A and B to eliminate x. And again, just trying to organize my work here. If I want to use these two equations to get rid of x one of the coefficients is going to stay a positive 3, but one's going to have to be a negative 3. So what I'm going to do is I'm going to take A, and I'm going to subtract B, which basically is multiplying B by a negative 1 and then adding the two together. So if I just take A minus B for my first step, I'm going to eliminate x's. So if I have 3x plus y plus z equal to 6, there's A. And now if I want to subtract B, that means multiply B by a negative, then B becomes a negative 3x, a positive 2y, a negative 2z equal to a negative 14. So when I put those together, the x's cancel. Then I have 1y and 2y, which makes 3y. 1z minus 2z leaves me negative 1z. And then 6 minus the 14 gives me a negative 8. And I'm going to call this equation, well, we used C already. I'm going to call this equation D because we're going to have to come back to that, okay? So I chose two equations to eliminate x. Now I need to pick two different equations and eliminate the same variable. So I already used equations A and B. My options for the next step would be to use either A and C or B and C. And it really doesn't matter as long as it's not A and B again. So I'm just going to choose A and C, and I can use the same process where if I leave A unchanged, multiply C by a negative, the x's will cancel. So my next step, I'm going to take A and negative 1 times C and put those two together. So A was 3x plus y plus z equal to 6, unchanged. And then C gets multiplied by a negative. So if I multiply C by a negative, I get a negative 3x, a negative 3y, a positive 3z, and that's going to be equal to a positive 6. So when I combine these two equations, again, the x's cancel. That was the goal. Positive 1 and negative 3 gives me negative 2y. 1 and 3 gives me positive 4z. And then 6 and 6 makes 12 here. And I'm going to call this equation E. Now, if I'm looking at D and E, the results of those two eliminating processes, I have a 2-by-2 system. I now have two equations and two variables. So I can use elimination with D and E to solve for one of the variables. Now, looking at D and E, it looks like it's going to be easier to eliminate z because the least common multiple for their coefficients. If I'm looking at a coefficient of 1 here and 4 in the other equation, all I got to do is multiply the first equation by 4. So what I'm going to do in my next step is I'm going to do 4 times equation D, because that's going to give me a negative 4 for my coefficient here, and I'm going to add that to E, to the positive 4 that I have here. So 4 times D plus E is going to be my next step. 4 times D plus E. And you know what? I'm going to move this down here. So 4 times D plus E. Turn the pen back on. 4 times D plus E. Okay, 4 times D is going to give me 12y minus 4z equal to 4 times negative 8 would be a negative 32. E is not being changed here, so I'm just bringing down negative 2y, positive 4z, and positive 12. And now when I add these two together, those cancel. So 12 minus 2 gives me 10y, negative 32 and positive 12 gives me negative 20. And now I see here my first part of the solution. If I divide negative 20 by 10, I get negative 2 for y. So now I have the first part of the solution, and it's just going to be a process of substituting that back in to solve for the remaining variables. So I've solved for y, and now I'm going to plug into either D or E to figure out the value for z. So I'm going to take negative 2 and plug it into, I'm just going to choose D, although D or E would be fine. If I take it and let's say I plug it in here, 3 times y, which was negative 2. Actually, I think for spacing, I'm going to plug into E. Okay, so I'm going to take the negative 2 and plug it into E. So I have negative 2 times y, which we just found was negative 2, plus 4 times some value for z that we're going to figure out in a second has to equal 12. So that's 4 plus 4z equals 12. If I subtract over the 4 from both sides, then now I have 4z equal to 8. And then if I divide both sides by 4, then z has to equal 2. So now I have a value for y and a value for z. Now I'm going to take both of those and plug back into one of my original equations, either a, b, or c. So now I'm going to go into, let's see, I need a new color. I guess I can use green. I'm going to take the value for y and the value for z and plug into any of my original equations. I'm just going to choose a. So I have 3 times x, I still don't know, plus y, which we just found was -2, and plus z, which we found was +2. That has to all equal 6. So the +2 and -2 cancel. That means 3x has to equal 6, which means x has to equal +2. And now we have it, a value for x, a value for y, and a value for z. So our final solution here is going to be the x value, the y value, and then the z value. And there it is. And just like we did with the very first problem on our note sheet here, if we wanted to plug all those into each of the equations, we could verify that that's actually the solution. Okay? It's a lot of work, but as long as you're organized with it, it's not too terrible. It's actually kind of manageable. Let me just make a little barrier here. Okay? So we're going to try that again with these new equations. And feel free to pause the video and give this a try on your own if you're feeling pretty confident. And then you can come back and see if you did it right. So again, just for organizational purposes, I'm going to call this A, and this B, and this C. Maybe I should turn off this shape tool. Okay, so A, B, and C. So I need to pick 2 equations and get rid of a variable. Now the easiest variable when I'm looking at these to get rid of seems to be the y, because I don't have to change anything in the first 2 equations, for example, to get those to eliminate. So I'm just going to add A and B in my first step here. So A is not changing, B is not changing. I'm just going to combine them together as is. So x, y, z equals 6, 2x minus y, and 2z equals 6. So when I put these together, the y's cancel. 1 and 2 gives me 3x. 1 and 2 over here gives me 3z as well. And then 6 and 6 on the other side gives me 12. And we're going to call this equation D. So now I need to pick 2 different equations and eliminate the same variable. So I used A and B. In the next step, I can use A and C or B and C and get rid of y's again. So I'm going to choose B and C this time because adding B and C as is will make those y's go away without having to multiply. So B plus C. B is not changing. 2x minus y plus 2z equals 6. And c is not changing. Negative x plus y plus 3z equals 6. Just kidding, doesn't equal 6, it equals 10. And if I put these together again, the y is the same variable, goes away, which is exactly what I wanted. So now 2 minus 1 leaves me an x. 2 and 2. Hold on. B, yeah, okay, can't read my own writing here. 2 and 3 gives me 5z here, and then 6 and 10 gives me 16 on this side. So I'm looking at, again, calling this E, 2 new equations now with the same 2 variables. So now it's a process of elimination once again. So looking at these 2 equations, I would choose to eliminate x's, because I can multiply E by a -3, which would give me a -3 here to cancel with the +3 that's here. So in this next step, I'm going to take D as is, multiply E by a -3. So I'm combining D with -3E. So D, not changing, is, oh, let me change colors. This is all becoming one big blob of algebra here. So D as is, 3, sorry. I'm taking D as is, and I'm subtracting 3 times E, or adding a -3 times E, either way you want to look at that. So D was 3x plus 3z equals 12. If I multiply E by a -3, then I get a -3x, -15z, and a negative, what am I multiplying by again? 3. This would be 48 over here. Putting these together, x's cancel, +3 and -15 gives me -12 in front of z, and then -48 +12 gives me a -36, and then dividing both sides here by -12, I get z equals +3. So that's the first part of my answer. Now I'm going to substitute that back in. So that can go into either D or E. I'm just going to choose to plug it in here to D. So I have x plus 5z, which we just found was 3. That has to equal 16. So x plus 15 has to equal 16. If I subtract that 15 over, then x has to equal 1. And now I have 2 parts to my solution, which I'm going to plug back into either A or B or C. I'm just going to choose to take both of those and plug them into, let's just go to C. Actually, it doesn't matter which one you choose, but I'm going to go into A because there's no coefficients there, which make the work just a smidge easier. So x, which we found was 1, plus y, we still don't know, plus z, which we found was 3, has to equal 6. So 1 and 3 makes 4. That means y plus 4 has to equal 6. Subtracting the 4 over means y has to equal 2. So our solution for this system is 1 for x, 2 for y, 3 for z. So 1, then 2, and then 3. And again, if you wanted to, which I wouldn't every time, but if you were taking a quiz or something you wanted to verify, plug in the x, y, z into all 3 of those equations, and we're going to find that they make all 3 equations true. Okay? So not the prettiest, but if you stay organized, it's just a process of elimination. Get your 3 by 3 down to a 2 by 2, solve for one of the variables, and back substitution in from there. Okay? So those are pretty straightforward cases where things work out how they are intended to work out. But as we saw yesterday, there are a few special cases. There are the special cases where you get either no solutions possible or infinitely many solutions possible. So I just want to show you algebraically how those are going to, how they're going to look. So let's start this the same way. I'm going to call this A, because at first glance you're not going to be able to tell that these are a special case. I mean, it looks just like the others. And let's pick 2 equations, pick a variable to get rid of. Like, if I'm looking at A and C, I can add those together and get rid of the x's right away. So I'm going to take A, and I'm going to add C. Now, when I add A and C as is, the negative 4x, positive 7y, negative 3z equals 1, and 4x minus 7y plus 3z equals 6. What happens? Well, not only do the x's cancel, but the y's cancel, and the z's cancel, which means technically on the left side of the equation I have nothing left. 0 is the number for nothing. And my equal sign comes down, and then I have 1 plus 6, which is 7. So anytime the variables cancel from both sides in this process, that's when you have one of your special cases. So just like yesterday, we're looking at, is the statement remaining here, is it a false statement, meaning no solution, or is it a true statement, meaning infinitely many solutions? So 0 is never equal to 7. So since this is false, since 0 can never equal 7, the system can never have a solution. So there's no solution here. No solution here. Or we can also say that this system is inconsistent. So it would be totally acceptable to say either one of these things. Okay? So we're looking for variables to cancel in one of these special cases. And again, feel free to pause and see what's happening on the next one. Try it out if you want and come back and see if you've done it correctly. I'm going to keep working here. So again, maybe at first glance you're not noticing anything happening here. So we start the same way. We label these out. Pick 2 equations to get rid of a variable. Looks pretty easy to get rid of, x's or y's or z's using A and B. So again, I'm going to just combine these first 2 equations. So 2x, negative 3y, plus z equals 4. And then we combine that with a negative 2x, positive 3y, minus z equals negative 4. And putting these together makes everything cancel. Now technically that means nothing left on this side, nothing left on that side. 0 equals 0. And because this one is a true statement, so since this is true, we have infinitely many solutions. Infinitely many solutions. Or we can also say that this is a dependent system. The system is dependent. I guess I should put the word system in there. Okay, inconsistent system here as well. Although saying dependent system or saying infinitely many solutions both would be acceptable as answers. Okay, so you're looking for those variables to cancel in those special cases, and then the leftover statement's going to tell you whether or not you've got the no solution or the infinitely many. All right, now looking at the next one, We actually have a 4 by 4 system. We've got 4 equations and 4 different variables, x, y, z, and w. And we would go through the same process if these equations were worse, if there's a little more to each of them. We would take the 4 by 4, get it down to a 3 by 3, take the 3 by 3, get it down to a 2 by 2, and then back substitution once we've got the one solution. But this one works out a little bit nicer. Maybe you can see why. If you look at the very last equation here, all we have to do is divide both sides by 11 to find the first part of the solution. So I can see right away that w has to equal 2. And then I'm going to take that w equals 2 and just back substitute it in to continue to solve. So we take that and put it here. Then I have 3z plus 2 times w, which we just found was 2, has to equal 1. That means 3z plus 4 equals 1. If I subtract the 4 over, then 3z has to equal negative 3, which means z has to equal negative 1. So now I know 2 solutions. I'm going to take the w and the z and plug into the next level up here. So we're looking at 2y minus z, which we just found was a negative 1, minus w, which was 2. That has to equal 9. So 2y plus 1 minus 2 equals 9. 1 and negative 2 makes negative 1. If I add that 1 over, then 2y has to equal 10. And then dividing, we see that y has to equal 5. Okay, almost there. So now we've got w, y, and z. We're going to take all of those and plug into our last equation. So all of those get plugged in here. So we're looking at a negative x and a positive y, so plus 5, positive z, so minus 1, and then a positive w, so plus 2 has to equal 9. So negative x plus 5 minus 1 is 4, 4 plus 2 is 6, so plus 6 has to equal 9. If I subtract the 6 over, then negative x has to equal 3. If I divide the negative, then x has to equal a negative 3. And then our solution, we're going to write as what looks like an ordered pair. It's x, y, z, and w, and basically just going in the same order that our equations go. So I can see in the first one it's x, then y, then z, then w. So the solution is going to be a negative 3 for x, 5 for y, negative 1 for z, and then 2 for w. Okay, so this is just using back substitution. So you substitute back into the next equation, then substitute 2 answers back into the other, and end up with your final solution. So all the elimination steps can be ixnayed there. All right. So I showed you how to do a lot of this stuff by hand. I guess the question you've probably been waiting for was, can Desmos do this for you? And the answer is, fortunately, yes. Although you have to be a little tricky about it. So you're going to type each equation into a separate line. After the last equation, you're going to hit add slider. And don't worry, I'll show you this in a second. And then you're going to basically move the slider around until all 3 lines intersect. And the point of intersection is going to show you solutions for x and y. And then the slider is going to show you the solution for z. And now if it was an x, y, z, and w, you'd have to add 2 sliders, but I'm not going to ask you to do that. So I'm going to show you these steps that I just mentioned here I'm going to go back to the front here just to verify for this first system that we looked at here. So let me get my, oh, I didn't pull Desmos in. Son of a, okay, give me a sec here, folks. Don't mind my million tabs open. And I might have been a little more prepared. Okay, so now, really, no, technology doesn't like me sometimes. Okay, I'm going to be able to show you on both at the same time. Okay, so I'm going to type in the first equation into the first line. So I have 3x plus y plus z. I'm going to put on my keyboard. And then equals 6. Okay, next line, next equation. 3x minus 2y plus 2z equals 14. Next line, next equation. 3x plus 3y minus 3z, oops, 3z. And that's going to equal -6. Okay, so once you have your three equations in there, you see underneath each of them it says add slider. We don't want to do it every time. We just want to add slider once. So after the last one, I'm going to tap where it says add slider. Let me try that again. Add slider z. Okay, so now you should see your three equations and then a fourth box where it's given a value for z. Now what Desmos is basically doing here is it's going to guess at a value for z. And if you put your finger right on the blue dot there, you can move the slider around. That means you can move z around, or move your three equations around until you get all three of the lines to intersect at the same spot. So looks like right there. Oops, I missed it. The x, now I know the z value is 2, right, because we solved by hand. I just want to, okay. Maybe your finger can be a little more precise than mine. Son of a... Okay, I'm having issues here, people. You can see. Okay, try this again. So you're there we go. It happens and then it moves. You see what I'm struggling with? Okay, I give up. Well, you know the z was supposed to equal 2. So you're sliding it around till you get all those equations to match up, to intersect here. And then if you tap on the intersection, as I did up here, you can't see what I'm doing, but you see that 2, -2 popped up. So that's the x value and the y value in the solution. And we can see from our notes here that 2 and -2 were the x and the y in that solution. And then in the box where we have the z, we have the solution for z. So you move z around. It's basically guessing at z. It's saying, I don't know what z is going to be, but I'm going to keep plugging it in different values. And once I get all those equations to be the same, then that has to be the correct value for z. And if you took z out of each of these three equations, what you'd have is 3 linear equations. So making z a constant, right, guessing at z, makes 3 lines that we can find the intersection of. Okay? So you can type your 3x3 system into Desmos and add a slider for z, that means basically guess at z, move it around so you get all three to intersect, and then the slider value shows you that last part of the solution, and the intersection on the graph shows you the solutions for x and y. Now just so you can see with our special cases, let me put this away for a second. Okay, so here, the special cases, they still work the same way. I just want to make sure you can see it. So we had -4x, plus 7y, and then -3z equal to 1. Put in 3x plus y minus 2z equal to 4, and 4x minus 7y plus 3z equals 6. Okay, add a slider. And what you're going to notice here when you add the slider in is that those first two, actually it's the first and the third one, they're parallel. It doesn't matter what you do to this system, there's no way we can get all of those 3 lines to cross, because 2 of them are going to be parallel no matter what. So you can see here exactly as we said, there's not going to be a solution. Okay, so let me show you this last special case. What does it look like when there's infinitely many solutions? If we make this, I should have did this last time. 2 in front of x, -3 in front of y, and 1 in front of z, oops, plus 1z equal to 4, and then -2 in front of x, +3 in front of y, and then -1 in front of z equal to a -4, and then lastly 6x minus 9y plus 3z equal to 12. Okay, so in the same thing here, I have this slider. It doesn't matter, all 3 of those equations, they're all the same equation, so you can't even see a distinction here. They're all the exact same equation. Doesn't matter what we do, they're all matching up every single time. So again, we can see that there's infinitely many solutions in that case. Okay, let's put that aside for a second. All right, so we got one last problem here, an application problem. Same solving process. What we got to do is get 3 equations out of this scenario. So Monica has $106 in ones, fives, and tens. Those are going to be our 3 variables. 18 bills total, and she has half as many ones as she has fives and tens combined. So we got 3 variables. I guess I forgot to ask a question here. The goal would be to figure out how many of each does she have. How many of each bill does she have? Not sure how I missed to ask the question, but there it is. Okay, so I don't know how many ones, I'm going to call them x's. I don't know how many fives, I'm going to call them y's. And I don't know how many tens, I'm going to call those z's. But I know there are 18 bills total. So my first equation is going to be for the number of bills. Okay, number of bills. I don't know how many ones, how many fives, how many tens, but there are 18 bills altogether. And then the next equation is going to be for this total value here. Let me underline this one in blue. There were 18 bills. Okay, total value is $106. So a second equation for the value, or like the price per bill or something like this. So it's $1 for every one, plus $5 for every y, plus $10 for every z, for a total of $106. And then the last equation is the tough one. It comes from this last sentence. It says she has half as many ones as she has fives and tens combined. So the number of ones is half of the fives and tens combined. So ones, which we call x's, is half of the fives and tens combined. That's the y's and the z's combined. Okay? So a little tricky, but again, the number of ones is half of the fives and tens combined. Now, we don't have to worry about doing any work by hand. Good thing, because I didn't give you any space. But I'm going to go ahead and pull Desmos up so we can see one more time how to work this. So we've got, start from scratch here, and I'm going to hit the little home button to fix my window. So we had x plus y plus z equal to, let's see, there are 18 bills, and then it's $1 for every x, plus $5 for every y, plus $10 for every z, equal to $106, 106, and then the x's were equal to 1/2, 1/2, get out of the denominator, and it was y's and z's combined. Y plus z, really? Pretty sure I said plus, didn't type a plus. Plus, come on. Okay, so got them all in there. After the last one, I'm going to tap on Z to put that slider in. And then, let's see, get all my lines in the picture. I need to try to get these guys to cross. And that's it. I got it. So at 6, 4 for x and 8 for z. So our solution is 6 and 4 and 8. All right, get rid of that. Move this actually. So our Desmos solution was 6 and 4 and 8. And that's definitely a total of 18 bills. If you multiplied 6 by 1 and 4 times 5 and 8 times 10, that would be $106. So we had 6 ones, 4 fives, and 8 tens. And there it is. All right, you survived another one. Hope this is helpful. As always, available. If you need me, just send me an email, and I do my best to help you out in whatever way I can.